We'll continue from where we stop. Thank you for joining. Thank you. My name is Samson Akimale, and uh, I'm the one championing this particular series, which we've been taking for quite some time. And it is a deliberate um, initiative to help people managers, and that is why it's called Discovery for People Managers, just to sharpen their understanding and build their data capability so much that their confidence in data increases as they deal with data every now and then. And much more than that, all decisions expected to be taken by managers or people who are leading people are supposed to be uh, based on data. So, ability to play around data, work around data, make sense of data without necessarily just passing by it or allowing it to just be the usual way or the traditional way people view data is the essential reason for this series, which is um, a follow up on the fact that there is a workforce analytics absorption gap. So, this Discovery for People Manager initiative is to help bridge that gap, and it's an element under the workforce analytics adoption framework, which is the solution we have created to solve the problem in workforce analytics adoption gap, which is a challenge or a problem. So permit me eh, to share my screen. We've come a long way. We started all the way from Excel, the use of Excel. We dealt extensively well uh, with that for quite a long time. And we are currently on the use of SQL, which is a powerful tool or element to deal with or to handle or manage relational databases, which is a very, very crucial database type in all organizations in the whole world. So even though we now have um, NoSQL databases, of course, SQL databases are still much more in high demand and use, and we will do well to gain mastery, even if it is just a bit, on what is expected of one in terms of uh, having the basic understanding in its use. So, sharing my screen. Yep. So this is the SQL um, environment where we've run a number of codes the last time, and we've brought up a number of what is it called? A number of tables, and we've manipulated them. Also, here is another table I'm trying to bring up to query from. So select from this. So after this, I can equally say select from this. So I think I didn't specify how many columns SQL was to select earlier. That was why I didn't bring it out. Yes, it has brought it out for the table called students now. Okay, so just going straight to the curriculum, and we can move from there as fast as possible. Yes, so last class we stopped at manipulating more briefly some of the SQL statements and codes that we have written. And we have covered quite some lessons in that, which has equally broadened our understanding on how to um, flexibly tweak SQL statement or query to answer different questions that will come up in a given analysis concerning tables. But today we want to move forward a bit into still same SQL, but this time around we want to see another superpower or another advanced functionality that SQL has got. So tool, we've been able to deal with tables individually and tables specifically dealing with a particular request. But much more than that, while we started SQL, or when we initially ventured into SQL, we did mention how SQL came into existence. It was built specifically to answer a particular question, which was a problem with the then existing types of databases. And they were called flat file. Yeah. So the origin of databases started with this, what we call flat file databases and all that. And flat file databases itself started with something like this when people were inscribing things in stones during any transaction, very, very, very ancient time, as early as 7th to 6th century BC. There was an advancement in that, and when paper was discovered with ink, that inscription or inscribing on stone uh, got advanced into the use of paper. Biro is now being, I mean, pen is now being used to write on paper when this was discovered. And much more after that, when computer was equally discovered, those things that look like creation of table and I mean rows and columns right from this stone down to this ledger-like book we are seeing, they can now be easily represented in a computer table this way. And you can have your rows and columns, and those rows can be as many as possible as it were too. But as time went by, flat file databases were now in two forms, especially in the computer age. So it could come more like an Excel file, just like what I show here, and it could come like a CSV file. And a CSV file is what we call comma separated value. So uh, in that case, the delimiter being used is comma. It could have been any delimiter that could have been used, but something is separating those values. In this case, the values are what we call attributes, and we also call them fields. But the layman understanding of them is what we call column. So in data science, fields are equally known as attributes. They are attributes of a particular given table, and they are also called column. They are commonly known as column, and that's why generally we say table is a combination of rows and columns. So those rows and columns actually mean something technical which we need to understand as time goes on. So for flat file database, they could come this way in form of CSV file. The delimiter could be comma, which makes it a CSV file. It could be any form of delimiter as it were. For instance, in this particular example we are seeing here, comma isn't the only delimiter that is being used. We can see a demarcation stroke also dividing different words from one another just to try to show to the computer that these are different fields. So consider them separate from each other if you are to represent them in a more clear table just like this. So all of this delimiting you are seeing comma and a vertical stroke are actually a line dividing column just as it is in Excel here. So those are the two forms we could have flat file. And there was a problem with the use of flat file. The problem was that if we now needed to ask more questions or request the data to answer as many questions as possible. It was realized that those question requests are making us to create as many more columns as possible just for the data to be able to answer the question. And as much as we can always do extra columns beyond what was originally coming with data, the more we have endless columns, the more difficult and cumbersome the data becomes in analyzing. And the more confusing it could also be when you are querying their data, even with the use of computer, it may not be able to understand really well what you are trying to talk about. So that's exactly what gave rise to another form of data representation in a table beyond these regular flat file formats. And that's what led to the creation of relational databases, which helps to still keep data in rows and columns. Don't get me wrong. Even relational databases, they still represent or position data in rows and columns, but they are not dependent on a single table. So you create a table, and the table has rows and columns for relational databases, but you are at liberty not to get yourself restricted to just a single table. You can create as many tables as possible as those questions are coming to mind. So you can create as many tables as possible. What is only required is ability to now link up all of those tables to make them have what we call relationship. That is where the word relational databases come from. So as much as you are now allowed to create many tables instead of creating many columns in a single table, you can create as many new tables as possible, and they have limited number of columns so that they can be more effectively managed. So long you are at liberty to create more tables instead of more columns, because you are creating columns can run into 120, 200 and what have you, and that's too large to even view at a glance. So keep the number of columns as brief and as small as possible, then you can have tables as many as possible. So as long as we are allowed to have as many tables as possible, those tables must be logically connected to one another, such that by picking the control of each table, you are able to pull out or extract data from more than one table at a time. And that's exactly what we are going to in today's session. We've before now query a single table. We explored a single table, try to use a single table to answer as many questions as possible, writing SQL queries. So we can see that in the previous recording to see how we dealt with that. But today, we are going a bit more advanced into what SQL has got to offer, in that SQL is now making us to delve into its value that makes it more useful and more valuable than flat file, in that you can have as many tables as possible in relational databases, and you can use SQL to query those things out. Then what are you now supposed to do? As much as you can have as many tables still on the same, meaning that a single data set can be split into many tables instead of making that single data set to have several columns. So instead of having several columns, I can just keep it small number of columns, 5, 6 is fine. Then instead of creating an extra column because of a new question that data is expected to answer, I would rather create a new table and name that table after the question that particular table is supposed to answer. Then you can just create a couple of columns for it. So, but there must now be a linkage between all tables you have now created from this singular table, such that when you need to pull out information from one of the tables and it is not actually there, but it is there, but you need to add another feature to that thing you want to pull out, but that is not in that particular current table, it's in another table. Then you have to find a way of pulling out that information or data from the two tables. And that can only be possible if you have linked up or joined all the tables created together appropriately. And that's exactly what today's discussion is about. So, yes, that takes us to chapter 7, which is now discussing more into structured queries and how we could combine as many tables as possible. So, objectives is to uh, build a process for us to be able to formulate a structured query such that we can extract and we can combine data from more than one table, meaning from multiple tables. So, we another objective now, that objective is now being broken down into these four sets. So the summary of them is okay. We want to formulate structure query to extract data, to combine data from different table and bring them out as if you have queried them from just a single table. And how do we go about that? We have to first explain the structure of relational databases. Even though this was mentioned when we started SQL afresh, but now we need to go a bit deeper and bring out that structure very well for one to understand. By the time you see how those structure relate very well, when you are writing query to bring it out, the logic forms better in your head because you know the structure of where you are requesting data from, and you know how to write the query, or that will rather help you how to write the query better because you know what the structure is. And the name of the structure we also get into it in the course of today's lesson. So we also create SQL queries using multiple data tables. We will use what we exactly call join. Join is an SQL statement, and that word is now joining queries dealing with two or more different tables and pulling out a report or returning an outcome that extract information from those more than one tables, and you see them live and direct. So we also try to describe how SQL is used to manage databases because SQL is the language you eventually use to manage your database, and that's what database administrators eventually do. What level of permission are you giving to some users on the database? How do you restrict the permission? Who is responsible for what? How do you check some logs to see who does what at what time? How do you delete some account? How do you downgrade some permission? How do you upgrade permission? How do you improve some stuffs right on your relational database using uh, structure query language? So those are the different things we will cover in this chapter 7, just to cap up all what we have done so far in SQL. Then after which we then move to the eighth module, which we'll be talking about another visualization tool, and that is Tableau. All right, we continue today. So, what is this relational database about, and what is the inherent technical feature it has got, which has made it quite um, indispensable in the world of data? In fact, some of the tools, anybody that says is into data science or is picking a fraction of data science, probably data analytics, is the fact that amongst all languages you will use or you want to learn, you cannot run away from SQL. And that's why our curriculum structure it in such that, okay, we started with just the common tool or application that people know about, or even though they don't use it to its full capacity. In this case, I'm talking about Excel. So we started with that just to see how we can test the water in the world of data gradually and then move up to what we are currently doing. So SQL is a very, very fundamental language. An average data person must have an idea of, because you can find yourself in any organization, and most of them they use databases that are backed up with relational databases, as it were. So ability to just play around a few things to know what to pull out and how to pull it out and what language to speak is very, very crucial. So after which we also move into another language if time still permits, or we can conclude this curriculum, as it were. So Relational databases in general are very powerful, and what makes them powerful is they have ability to store data, and they will store it across several or separate tables. But fundamentally, those tables are expected to be connected, and that's what I mentioned earlier. Something must link those tables together, and that is when whatever query or SQL statement you write, you'll be able to pull out or return an outcome that is accurate for you. If those tables are not linked together, then there is nothing you want to pull out. I'll get to that. How do we link different tables we create in relational databases together by writing an SQL statement or SQL code that will pull it out? So it is one thing to be able to write the SQL statement to pull those things out. It is entirely a different thing to make sure that the tables are already linked. So even though you are good at writing SQL statement, and writing SQL statement is even easier. How do I mean? It's easier in the sense that if you do not even know how to put the codes or statements together, you can just easily ask AI. AI has understanding of, I do not know what programming language AI cannot speak at the moment. That guy is that vast, because AI has been trained or is currently being trained with as many data as possible on per second basis. So there is hardly anything new to AI now that it doesn't understand, especially in terms of programming language. So there is nothing you want to write, you just specify, you just tell ChatGPT or any, okay, I want to query so thing out of my data set. This is the structure of my data set. It has this set of columns. I want to query this out. Give me a query statement or a programming language in SQL. It will give it to you within a twinkle of an eye. Give me same thing in Python language. It will give it to you so easily. Oh, I want to do it in Excel. What Excel function or formula will I use to achieve this same thing from this data set, assuming it is in Excel? It will give you immediately. So there is nothing as far as programming language is concerned that you'll not be able to easily get in terms of code writing and what have you. But beyond that, that code wouldn't work if the table you want to query from, or the table you want to subject that code or SQL statement to, the table you want to subject that statement to, are not connected. It will not work. It will just read out. It will give you some error. So the most fundamental thing is to ensure when those tables are being created, they are created in such a way that the linking element is available in each of them. So I have one table now. I'm creating another table. I am linking it up immediately with the existing one. By the time I'm creating the third table, I'm also either linking it to the second one, or I'm linking it to the first one. So at least the three of them are connected, either 1 to 3 or 1 to 2 or 2 to 3, whichever way they are connected. So the moment I now pick the linking element, it can then give me whatever query I want to bring out from me. So this structure helps reduce duplication. The structure of having as many tables as possible, or the structure of disaggregating a single table that could have had 100 columns, disaggregating it into several tables with smaller number of columns. It helps to prevent, or it helps to reduce duplication. It also helps to minimize what we call the risks of inconsistencies, because when a single table has too many columns, it becomes, by the time you are querying some things out of that table, number one, the database may slow down because it's trying to figure out how to work around the whole thing, and it may also create some inconsistencies in terms of recording and all that. And beyond that, it can also create redundancy, which is a major issue. An average data person want to ensure they are avoiding every now and then. So um, we will look into this, and we'll probably take a look at the examples we used previously, so that can easily drive home the point, as it were. So while having additional tables, they help to define all of the relationship that exists between the first table you have created, such that those tables are linked together correctly in one way or the other. So what am I trying to say? This is the picture of what exactly I was explaining in that relational databases. So we are trying to see what is the structure of relational database. So the name of the structure for every relational database, the name given to it technically is called schema. So when you see the word database schema, it's simply talking about database structure. Do not forget, all tables are resting on a database. So that is how relational databases are structured. So you can create database first and then create table. When you attempt to create table in a relational database using SQL statements, it will ask you, or not, it will ask you which database you want to put that table on. But if you are already on a particular database and you're already in the environment, it will assume that you are creating that table in that currently running database. So if you do not change the database and you create a new table, that table is automatically saved or belongs to that particular database. So if you are not intending to put that table in that database currently active, you have to change database or create a new database, then now create the table. So what I'm saying in essence is that anytime you are creating table, the table is automatically saved in the currently running database unless you specify otherwise. So if you do not specify otherwise, whatever table you are creating in an SQL environment, SQL takes it and makes it a baby of that currently running or currently active database. So for all these database, they have a structure, and the structure is what we call schema. Schema is how the different tables you are now creating on this database, how those tables relate to one another. Now, in the data world, we create table based on projects that we want to work on. For instance, this example you are seeing here, this structure is about uh, a project called movie. The project was about a movie, and it's about, okay, we want to see how this movie industry, how many movies are being watched, who are the actors of different movies, as people probably go to cinema to watch different movies, or maybe in the traditional age that people probably go to different centers to buy different movies already saved in different electronic device, whichever way, either directly with the movie industry or purchasing it in a particular outlet selling different movies, but it's about movies. And that is the project. Okay. And so we want to create a database for it. It begins originally with movies. So the very first table you want to create, as seen here, is you want to create a table that will be named movie. But beyond that, there are a lot of questions you want to ask in the process of trying to dissect and trying to dive as deep as possible into that movie project. So the very first table you create is called movie, and that table cannot store more than, okay, what is the movie title, and what exactly, probably what year was that movie produced. And having created that, that is not all what is going to happen about that movie. You also probably want to know, in this particular movie A, or before I go there, having created the table for the movie, and all the movies are listed by their name, in this case their titles A to Z, let's say just about 50 to 100. And of course we can equally easily list out the years they are produced. In that simple movie table, you must also be able to specify the the column or the attribute or the field that makes each of the movie title different from each other. Of course, the movie titles will be different because it is hard for movies to have exactly the same title. But that is not enough to distinguish one movie from another. Because incidentally, you can just have two movies having the same title and probably they were conceptualized differently. So, what the content of each of them is dealing with is slightly different. And of course, there are two different movies, but unfortunately, because they were conceptualized by two different people, they use same name, but the content is different. And you cannot in your own table give it a different name to make them different from one another. You have accidentally have two movies with the same name. And that is going to skew analysis. That is going to affect a lot of different exploration you want to do into the data because two different movie titles will be appearing as same. So that is why it is not advisable to use movie title as the distinguishing factor for each of the movie in that table. And that's exactly why you have what we call movie ID. So that movie ID is going to be the differentiating factor, something that is unique to each movie that is being listed on that table. So the ID can be a combination of any number, or you can start from zero and start numbering like that. So movie zero movie number zero or movie having ID zero would definitely be different from movie having ID one, two, three, and number that way. You can choose to have a two-digit or three-digit number just to identify those movies that way. But beyond that, some other things I want to do or that has to do with this movie cannot necessarily come inside this movie table again, just in the spirit of ensuring that, okay, you explore as many tables as possible just to keep each of the table as lean as possible. So I want to see, okay, which actor is actually is actually featuring in this particular table, or who is actually the director of this movie. So I do not necessarily have to create another column inside that same movie table. I can just create a new table entirely and I'll call it movie actor table. And in that table, I am now at liberty to list the the names of the authors that are featuring in that particular movie. But how do I do that? That is where the structure intent is coming up now. Now I'm beginning to break the different things that can come as a question in this movie data project up. Okay, I can have a question that will be asking me to query out movie actor table. So imagine if the table is as large as 20,000 or 50,000. I cannot deal with a single table again. But if I have it at another table and that one is dealing with the actor, that's fine. Okay. I also want to know the directors. I can have another table for that one too. I create another table for it, as you can see here. I can also want to see, okay, how much income has a particular movie generated in a particular month and in a particular year. And do not forget that same movie can make some income or revenue monthly or month in, month out, year in, year out, and keeps going that way. If there is no singular stuff differentiating that movie title or movie name will be appearing same month. I mean, in different months. The movie title appears, let's say the movie title is something we call Sword. Sword appears in January, but that Sword also has some sales in February. The title will remain the same. It is still Sword. So it keeps on like that. It keeps on like that. And even if it has movie ID, it will still follow that same movie ID. I'll get to that and explain how to deal with that. Then we also may want to know, okay, what are the different comments people have passed? What are the people's perspective on each of the movie? How do we know the sentiments people are having around this movie, such that we know which movie is selling at what season and why is it selling at that particular season and all that. So you can find I may come up with the comment, then grade the comment in form of score and all that, and also have dates. Then because we have actor and we have director, we know these are actually human beings. So we could have a separate table that deals with the names of actors and directors directly and just link it up to the other two tables dealing with actor and director, as it were. So this will give you a well disaggregated structure to view different tables, and when the number of entries for the movies are increasing even up to hundreds of thousands, you are damn sure that the table cannot get complicated, because you have broken down different attributes that could have constituted extra column in a single table. You have brought it into a separate table, and they can increase organically to whatever extent without creating inconsistencies, without creating redundancies, without making the database to get crashed down, as it were. So what do we now call schema? By way of definition, how do we define schema, or how do we I'll explain it. Okay, schema is, a database schema rather, is just another way of saying the database structure is uh, a way of defining how data is organized inside the structure of your tables, and these tables are located within your database. Now, relational databases in general use schemas that are well organized, and the structure of organization for those relational databases schemas are such that you have a table, the table has a name, and the table has rows and columns. And technically, rows are given a technical name, and the columns are also given a technical name. So a table combines rows and column, but the technical name for column is what we call field, because they are the new field we created to represent a particular attribute that we intend the database to explore further or be able to return when a query is issued. So that is field. So if I mention field in the course of our conversation, if I mention attributes, just know I'm talking about column, because essentially tables are made of rows and columns. So field, like I said, is just an attribute of a particular record, and fields are vertical while rows are horizontal, because fields are columns, and of course columns are vertical. So I have given a technical name to column. Another technical name for rows is what we call record. So record refers to rows in a table, and it is the representation of a complete observation that moves from left to right across a table. For fields, it moves from top to down across a table in a particular position or attributes. So rows represent observation, a complete observation that we have in a particular table. And that's an example that we are seeing here. The movie ideal itself is a column, and that is a field. The movie title is a column, it's also a field, it's an attribute. The movie year is also a column, is a field. I can equally create another column for months. I can equally create another column for income and what have you. But that is how it will be enlarging that table such that to get up to a point that it will go beyond. It will make it difficult to easily manage. So when you have an extra attribute you want to add as a column, you can as well just create a new table and make that attribute name to become the table name. Just create an ID for it, then put in that particular attribute as a column again. If there's any other related attribute, you can add it to that particular table, because it's only having just one or two columns. Now you can have up to 3 to 5. It's still manageable that way, unless what you want to add is essentially different from what that particular table is dealing with. Then you want to create a new table entirely to deal with that. So having said all of that about database schema and the fact that it combines rows and columns are field, they are attribute, and rows are records, and records are also called complete observation. And a particular point across rows and column, or a particular place where column and rows meet, is what we call a data point. For instance, if you see 1431 written here, is where row 1 and column 1 meets, and that is a data point. Where you see 2026 is also where row 3 and column 1 meets, and that's also a data point. So all databases recognizes all these critical points in a table or database, and that's what makes them to be able to return any answer to whatever question you have asked them through is a code or a statement or a programming language, as it were, because that's how the tables are structured. But beyond rows and columns, relational databases or a database schema records or helps us beyond giving us what a row or a column is. It also takes care of what we call keys, meaning for every database schema, there is a key, and the key is actually very key. This is an answer I was withholding earlier while I was discussing the linking of the different tables you have created, or the tables you have disaggregated a single table into. A way of linking them, connecting them, is to anchor them on keys. So the database schema doesn't only just show us columns and rows, it also takes records of keys. And I'll get into this key very soon. So we need this understanding very well so that by the time we start writing or we are populating our different tables, creating a new table, then creating some columns for the new table, you will understand better why those columns are created, because it is not just expected of you to just create table. You must create that table in such a way that it is linked with existing tables. That is when that table is recognized in that database. If a new table you created in a particular data project has no link with any existing table, then that table is just on its own. So there's no way or no day you want to rise up and say, okay, I need an answer, but I need two tables to answer this question, but the other table is not linked up. If you issue the query, it's not going to work because there is no existing linkage between the tables you are querying from. And that's what defines relational databases. You must establish the relationship between the tables. And a way of establishing the relationship is to connect them. The way to connect them is to use keys. And I'll get to the keys soon. So it's also define relationship between tables, or the relationship that exists between table, yeah. And it also help clarify the different data types and fields. We also get into the data types uh, hopefully by next session. So we have done data types before. I've discussed about integers. I could recall I've discussed about floats. I've also discussed about variable characters and what have you. So we've discussed at length about different data types, but we will go into them again and see their usefulness in a database schema, because what we call schema is a defined structure. And when you are defining structure, having set out rows and columns and also set up your keys, you also want to put extra layer of specification in terms of how many characters should a particular column contain, and that is a further instruction that shows that the database is actually well structured and the structure is defined. So if somebody comes in and is imputing data that does not conform to the specification, then the database will not accept it. It's also a form of control. So all these are quite very, very important for us to understand and see how they work. Okay, what are now the keys? Like I mentioned, don't forget. So the database schema does connection, and the connection is done through creation of keys. So what are the keys? So every database has a dual key, and the keys are, it is either it is a primary key, which is the most critical key, or it is a foreign key. Now, primary keys are the unique attributes. Don't forget, by unique attributes, I mean unique field in a table. More clearly, it means they are the unique column in a table. It means that column specifies and differentiates one row from another. Even if there are 1 million rows, that particular field or attribute, or what we call column, that we now call the primary key, has successfully differentiated each of the rows that exists in that particular table. Let me quickly give an example. Okay, here is the SQL environment, and we can see this here. I have a column called course, another column called age, another column called name. Then there's a column called ID. So at a glance, the primary key here, or the unique column in this particular table, is the column called ID, because it gives very, very distinguishing name to each of the rows, such that if you want to make reference to a particular row, all you need is to pick the ID number, and it will query it out for you without mixing it up with another row. But if you check some other attribute here, like the attribute called course, which is column name as course, one of the entries there, you see data science in number 6. We also see data science again in number 8. So that, what that means is that you cannot use that column to be the primary key for this table, because there are entries here that are not unique to a single row. There are more than one rows having the same value. That cannot act as a distinguishing factor. So that's exactly what I was trying to explain there. Okay, so the primary key helps in such a way that you can easily identify and differentiate one row from another, and they are called unique identifiers, such that when you pull them, they are only pulling the row you have specified without mixing it up with any other row. But one particular point of caution is that for very simple tables, or if you are freshly creating tables for a particular project you just started, um, the primary key for a particular table can be just one column. But as the table is being multiplied, it may not be necessarily easy to retain the unique identifier to be one. It may be a combination of more than one columns. I will explain that as we get along. So another key in database is what we call foreign key. So foreign key comes from the name, something that comes from another country that lands into my own country. Let's say between country A and B. If something moves from country A to country B, even though that particular thing is local to country A, the moment it moves from that country A and gets to country B, it becomes a foreign element. Just the same way in the medical world, doctors will tell you if anything that is not organically part of human body from birth, or as human body is structured, or as God has structured human body, whatever thing that is extraneous, that is not a tissue, it is not blood, it is not bone and what have you, but it's inside human body, they call it foreign objects. So for instance, let's say a baby mistakenly probably swallows a little pebble or something, like a small wood or whatever. That is considered as a foreign object, because that is not the local place for that particular object. It's in a foreign land entirely. So it's called foreign. In the same way, when you have an ID in a particular table, and that ID is meant for that table, the ID, or the unique identifier, is a primary key for that table. But when you now pull out that primary key from table A and is also featuring in table B, that particular unique identifier that was a primary key in table A where it's coming from, but it's now being also used in table B. The name is no longer a primary key in that table B. It assumes a new name, and the new name is now a foreign key. I give an example of that. In this particular table you are seeing, you can see where we started from. The beginning was creating a simple table for movie, and that should show us the movie title, show us what year the movie was produced. Then we just have a unique identifier for that table. We call it movie ID. Yes. So in this case, movie ID is the primary key of this table. But if this movie ID, for any reasons, appear in any other table we are seeing in this structure, it was originally primarily in movie table, but when it is used in another table as we are seeing here, the function is no longer primary key. It now becomes a foreign key in that table. So if you check table gross income, we still have movie ID there. The function it is performing here is never the function of a primary key, because it was imported from the original table that has it as primary. And that table is called movie. The ID there is movie ID, and it is the unique identifier, it is the primary key there. When you import it into another table bearing another name, in this case, gross income table, the movie ID key here is no longer primary key. It becomes a foreign key. It is imported from another local source. And that's exactly the function it's playing in every other place. We can see it here. It appears in four tables apart from movie table itself. So the function it is performing in those other four tables is never the primary key again. It is now performing the function of a foreign key. And now, another very important thing here is, after defining what primary key is, it is stated clearly that primary key can be a single column, as we have seen for that movie ID. That's a single column. And primary key can also be a combination of columns, meaning it can also be two columns combined together, acting as a primary key. And how that is done is this. For instance, in movie table, we have movie ID as the primary key. As we move up to gross income table, we also have movie ID there, but that is not the primary key, it's a foreign key. It is only used in that gross income table so that it can be linked to movie table. But what is now the primary key in gross income table? The primary key is such that what are the combination of columns that will help me pull out an entry, and that entry will be unique such that it has no duplicate or repetition. How do I mean? In gross income table, if you check it very well, there will be a movie ID repetition, because the gross income table is having months and is having year. A particular movie can have sales all across the years, January, February, March, down to December. and the movie ID will not be different. So a single movie ID will repeat itself in this gross income table more than once. And we have said that no single column should have the same ID. In movie table, the ID will never be the same. It will be unique. But in gross income table, because movie ID is never the primary key, you will have you have same movie ID appearing more than one times. So how do we now identify the primary key that differentiates a single set of observation as primary in a gross income table? Number one, it would be a combination of more than one column now. It will take care of, it will take the movie ID column one. It will also take the column called months, and it will also take the column called year. So it is impossible for a particular movie ID to to have sales in a particular month and a particular year. Those three things will combine together to differentiate that same movie ID that will reoccur for another month. What I'm saying is that a given movie ID 001 sold in January 01 in year 2000, that gross income table, we see it as a single entry, even if it is having similar movie ID with a same movie ID that is now sold in February that same year. So at least one of the three things will differentiate one movie ID from another, and those three will now be the primary key for that table called gross income. And that's why it was said earlier that sometimes you will see primary key just being a single column. You just need to check it. In another table, it cannot be a single column because you have already seen a previous primary key somewhere being imported into that table. Then necessarily it has to combine with another column to make a unique identifier or identification for that particular table. So that's exactly what this particular statement is talking about here. Then I've also explained what foreign key is, and foreign key is still a primary key somewhere at a local stage, and when it gets into another table, it becomes a foreign key. It is no longer acting as a primary key, so it has to combine with a couple of things in that new table, and their combination, two of them or three of them, will now combine together to become the primary key for that new table. So that is why it is said in advance that primary keys can be just single table, and it can be combination of more than one tables. So, and this is the further explanation. In this particular place, I have a gross income. So let's now say that, okay, I want to have gross income, but I want it to be disaggregated along country, meaning that let me see the income made from this particular movie title for some set of countries. I want to know which country is selling this more than the other country. So you can create another table now called gross income country. The only thing differentiating it is just the fact that we want to see country now imputed, and that's why country is included in this one. So you can see, to have the primary key for gross income country table now, the primary key will be different from the primary key in gross income. So the other one was having movie ID, month, and year as primary key, which was for gross income. But for gross income country, the primary key will now be still the same combination of the previous primary key, which was a combination of three things: movie ID, month, and year. That's the primary key for the gross income table. Now, this one is adding extra layer to it. The primary key for gross income country will now be movie ID, month, year, and country. So those four columns have to be combined together before you can determine a unique identifier in this particular table. And same thing goes for any other attributes we want to choose or see as it is. So those are the things we need to bear in mind and be able to put into action when there is need to execute one thing or the other. So in following sessions, we will look into um, the use of SQL with multiple tables, practical demonstration that will combine SQL functions to extract as much data as possible. We'll do some management features for SQL and some other alternatives. Then we will equally have a summary of what we have done so far in SQL plus the other set of things we have done. I will take input and questions at this point, if any. And in the absence of none, we will call it a session. Let me know if you have any question. So for quick reference and to be able to um, keep yourself abreast of the few sessions we have done, you could get them on our social media language, especially on the YouTube. So you could watch as many sessions as possible just to see the progressions we have undertaken so far. So if there is no other question, then we can call it a session for today. Thank you, Esther. Thank you, everyone, for joining. See you next session. Uh, if you have another quick, thank you, Biodun. Thank you, everyone, and have a lovely week ahead for yourself.